Imagine you're building a robot that can think and react to its environment. It needs to detect whether an object lies inside a specific zone, let's say a circular boundary, but instead of hard-coding the logic with geometry, what if your robot could learn this on its own? That's exactly what we're doing today. We're building a feedforward neural network from scratch in pure C++. No frameworks, no libraries, just raw powerful code. You'll see how simple inputs like coordinates x and y can pass through layers of neurons to predict whether a point lies inside or outside the circle. And all of it will be learned through training. This is the first part of a full series where we built a feedforward neural network from scratch. In this video, we'll focus on the foundational components like weight initialization and activation functions. In the second video, we'll implement forward propagation and back propagation. And in the third, we'll test and evaluate the model. By the end of this video, you'll understand the fundamental building blocks of a neural network, weight initialization and activation functions. All written in pure C++. No magic, just clear structured code that will set the foundation for more advanced models down the line. So grab your C++ editor, hit that like button, and let's bring this neural network to life. Let's get started. First, we're including some standard libraries that we'll need for the project. And here's the first one, hash include iostream for input-output operations, and hash include vector to handle dynamic arrays, and hash include cmath for mathematical operations like exponentials and powers. And the next one is hash include random for generating random numbers to initialize the weights. Then we have hash include std except for handling exceptions. And the last one is hash include chrono. Chrono will help us measure the training time later. And we're using the std namespace to simplify the code a bit. Using namespace std. Now that we're diving into the code, the first thing we'll do is create a namespace called activation. Think of a namespace like a container that helps us organize our functions. It's especially useful when we want to group related functions together, keeping our code clean and easy to manage. In this case, we're building functions for activation and their derivatives. These are mathematical operations that introduce nonlinearity into our neural network, which is crucial for learning complex patterns. So we say namespace activation. And inside the activation namespace, we'll implement two common activation functions, ReLU and Sigmoid. Alright, now let's write our first activation function. Inline double ReLU, and it takes double x and it will return max 0.0 and x. ReLU, short for rectify linear unit, is a simple but powerful activation function. It returns the input x if it's positive and 0 otherwise. By introducing this nonlinearity, ReLU helps the neural network learn more complex patterns and makes training faster compared to other activation functions. And the inline keyword in C++ is used to suggest to the compiler that it should insert the function's code directly at the point where the function is called, rather than generating a separate function call. Since ReLU is a simple one-line function, using inline can help improve and speed up performance by avoiding the overhead of a function call. Now that we have defined the ReLU function, the next step is to write its derivative. During backpropagation, we calculate gradients using derivatives to adjust the network's weights and improve learning. Here is how the derivative of ReLU looks. Inline, double, ReLU, derivative, and it takes double x, and it will return inside parentheses x greater than 0, question mark, 1.0, colon, 0.0. It's simple. If the input x is greater than 0, the derivative is 1. This means the neuron is actively contributing to the learning process. But if x is 0 or negative, the derivative becomes 0, and no gradient flows through that neuron, effectively stopping it from contributing to learning. Next, we're going to implement another activation function called the Sigmoid function. Unlike ReLU, which is mainly used in hidden layers, the Sigmoid function is often used in the output layers, especially for binary classification tasks, like our problem of determining whether a point is inside or outside the circle. Here's how the Sigmoid function looks in code. Inline, double, sigmoid, and it takes double x, and it will return 1.0 divided by, inside parentheses, 1.0 plus x pof negative x. The reason we often use sigmoid in the output layer is that the sigmoid function maps any values between 0 and 1, making it great for probability-based outputs. In our case, it will help the network decide whether a point is inside the circle, 1, or outside the circle, 0. Next, let's have its derivative. Inline, double, sigmoid, derivative, and it takes double x, and here we declare a variable to have the sigmoid of x. So we say double s is equal to sigmoid, and we pass it x. Then it returns s times, inside parentheses, 1.0 minus s. This is the derivative of the sigmoid function. We use this derivative during backpropagation to calculate how much each weight should adjust to minimize the error, the difference between the model's prediction and the actual value. Its smooth gradient makes it useful for binary classification tasks, providing clear feedback for the network to learn from. And the next step is to create a matrix class. Neural networks involve a lot of mathematical operations with matrices, from storing weights and biases to performing calculations during forward and backward passes. Instead of using external libraries, we're building our own lightweight matrix class from scratch, keeping things simple and efficient. Let's start by defining the class and its basic structure. Class, matrix. Here, we're using a 2D vector to store our matrix values, and it's private. So private vector double data, and two variables, rows and cols, to keep track of its dimensions. Size underscore t, rows, comma, cols. Next, we'll add a constructor to initialize the matrix with the specified number of rows and columns and set all of the elements to 0. And we say public matrix, and it takes size underscore t r, size underscore t c, colon, rows inside parentheses r, comma, cols inside parentheses c. And inside the constructor, data dot resize, and we pass it r, comma, vector, double, and inside parentheses, c, comma, 0.0. This ensures that every matrix we create starts with clean zero initialized values. Next, we define the function call operator, parentheses, which lets us access and modify matrix elements using row and column indices, just like a 2D array. And here we say double reference operator, parentheses, which means it will return a reference, and it takes size underscore t I, comma, size underscore t j, and it will return data square brackets I and square brackets j. Now we define a const overload of the function call operator. This version is nearly identical to the previous one, but with an important difference. It's marked as a const at the end. And here we say const double reference operator, parentheses, which means the function returns a reference to a const double, and it takes size underscore t I, comma, size underscore t j, and another const here, which means the function itself does not modify the object, and it will return data square brackets I square brackets j. This ensures that when we access the matrix element using a const matrix object, the function generates read-only access. It prevents accidental modification, making our code safer. Now, let's add two simple but essential methods to retrieve the number of rows and columns in our matrix. And here's the first one. Size underscore t, get rows, const, and it will return rows. And the next one is size underscore t, get calls, const, and it will return calls. Okay, that's it for the matrix class. Now it's time to build the core of our project, the neural network class. This class will handle everything from defining the network structure to performing forward propagation, back propagation, and training. And we start with the class definition. Class neural network. The neural network class stores the network's architecture, including the number of layers, neurons per layer, and the weights connecting them. It will also include methods for key operations like forward propagation, back propagation, and training. Let's begin by declaring the essential variables that define the structure of our neural network. First, we define our private members, and the first one is layer sizes, a vector of integers. And here we say vector int layer sizes. It stores the number of neurons in each layer of our neural network, defining its overall structure. Next, we declare three private member variables, weights 1, weights 2, and weights 3. So we say matrix weights 1, weights 2, and comma weights 3. These are instances of our matrix class, and will store the weight values for different layers of our neural network. Next, we define three vectors, bias 1, bias 2, and bias 3. Vector double bias 1, comma bias 2, comma bias 3. And these store the bias values for the different layers of our neural network. Now we need to declare a Mersenne twister random number generator. And here we say empty 1993 7, and we're gonna call it gen. This will be used to initialize the weights with random values. Now that we have our network structure in place, we need to initialize the weights. Proper weight initialization is crucial for ensuring efficient learning and preventing issues like slow convergence or vanishing gradients. I'm gonna make a video about this in the future. Let's define a method to handle this. Void initialize weights. This method will randomly assign initial values to our weight matrices. Random initialization helps break symmetry between neurons, allowing them to learn different patterns instead of all updating identically. Alright, let's move on to something that will help us generate random numbers, which we'll use for weight initialization in our neural network. This is where randomness comes into play in our network setup. Here, we're creating a normal distribution object. Normal underscore distribution dist 0.0 and comma 1.0. But what does that mean exactly? Let me explain. A normal distribution is a bell curve where most of the generated random values are clustered around the mean value and get less frequent as we move away from the center. In this case, our mean is set to 0 and will generate values with a standard deviation of 1.0. This is useful for randomly initializing weights in our neural network, ensuring that the values are centered around 0, something that helps in preventing any initial bias toward positive or negative values. Now, let's add an important step in our weight initialization. Instead of just using random values from the normal distribution, we need to scale them properly. This helps the network learn efficiently by keeping the values within a reasonable range. And here's the code. Double scale 1 equals square root of 2.0 divided by layer sizes bracket 0. And for the next layer, we say double scale 2 equals square root of 2.0 divided by layer sizes bracket 1. And double scale 3 equals square root of 2.0 divided by layer sizes bracket 2. But what's happening here? This formula is based on He initialization, which is designed to prevent issues like vanishing gradients or slow convergence when training deep networks. He initialization is a method for initializing the weights of a neural network to help it train efficiently, and is specifically designed for activation functions like ReLU. The formula is simple. We divide 2 by the number of neurons in each layer and take the square root. This scaling ensures that the weights are neither too large nor too small, helping our network train efficiently and stably. Now that we have our weight matrices and scaling factors set up, it's time to initialize the weights using He initialization. We'll iterate over each weight matrix and assign values drawn from our normal distribution scaled appropriately. Let's start with the first weight matrix, weights 1. We use a nested loop to go through every element in the matrix. For int I equals 0, I less than weights 1 dot get rows and I plus plus. For int j equals 0 less than weights 1 dot get calls j plus plus. Then we say weights 1 I comma j equals dist gen times scale 1. And we do the same for the next layer. For int I equals 0, I less than weights 2 dot get rows, and I plus plus. For int j equals 0, j less than weights 2 dot get calls j plus plus, and weights 2 I comma j equals dist gen times scale 2. And for the last layer, for int I equals 0, I less than weights 3 dot get rows I plus plus. For int j equals 0, j less than weights 3 dot get calls j plus plus. Weight 3 I comma j equals dist gen times scale 3. Now we need to set up the biases. Unlike weights, which are initialized with small random values, biases are typically set to 0 at the start of training. We'll use the fill function to set all the elements of bias 1, bias 2, and bias 3 to 0.0. This ensures that each neuron starts with no initial bias, allowing the network to learn from the data without any predefined preference. So here we say fill bias 1 dot begin comma bias 1 dot end comma 0.0, and we do the same for bias 2 and bias 3. Fill bias 2 dot begin comma bias 2 dot end 0.0, and fill bias 3 dot begin comma bias 3 dot end 0.0. This step is important because biases help neurons activate even when all weighted inputs sum to 0. During training, these biases will adjust to optimize the network's predictions. Now, let's define the constructor for our neural network class. This will allow us to create a neural network with a customizable structure by specifying the number of neurons in each layer. And here we say public neural network, and it takes int input size comma int hidden size comma int hidden 2 size and comma int output size. Inside the constructor, before the constructor's body, we use an initializer list to set up our neural network components efficiently. And here we say colon, layer sizes, curly brackets, input size, comma hidden 1 size, comma hidden 2 size, and output size. This stores the number of neurons in each layer. Next, weights 1, and we're gonna pass it input size and hidden 1 size. And we do the same for the next layer, weights 2, hidden 1 size, comma, hidden 2 size. And weights 3, hidden 2 size, comma, output size. This part of the code initializes weight matrices for connections between layers. Then we say bias 1 inside parentheses, hidden 1 size, comma, bias 2, hidden 2 size, bias 3, output size. And this part of the code creates bias vectors for each layer. And the last thing we do, gen inside parentheses random underscore device curly brackets parentheses. And this sees the random number generator for weight initialization. Random underscore device is a special class in C++ that generates truly random numbers from hardware entropy. With this setup, our neural network is structured and ready for initialization. Now inside the constructor, we need to ensure that the neural network is initialized with a valid layer sizes. A neural network can have 0 or negative neurons in any layer. So we add a simple check like this. If input size less than equals 0 or hidden 1 size less than equals 0 or hidden 2 size less than equals 0 or output size less than equals 0. And here we throw an exception. Throw invalid underscore argument, and inside parentheses we pass it this message. Layer sizes must be positive. And finally, we call initialize weights to set up our network's weight matrices and biases. So initialize weights. Alright, that's it for today's video. If you found this video helpful, be sure to hit that like button, subscribe, and ring the bell so you don't miss the next part of our series. In the next video, we'll be diving into forward propagation and implementing back propagation with gradient descent, taking our neural network to the next level. You won't want to miss it. Thanks for watching, and as always, stay tuned for more. Let's keep building this neural network together. See you in the next one.